In this class, let us learn Huygens principle. This principle helps us to determine the shape of a wavefront at a later time from a given wavefront. According to this principle, each point of the given wavefront acts as a source of secondary waves, and they travel in all directions with the speed of wave. Since each point is a source, it gives out spherical waves. These spherical waves are referred to as secondary wavelets. The new wavefront at a later time is given by the forward envelope of secondary wavelets, or a common tangent to all these spheres gives the new wavefront. Let us consider a spherical wavefront. The point A of the spherical wavefront acts as a source of secondary waves. So it gives out disturbance or energy in all directions which travel with the speed of wave. So the wavefront of this point will be a sphere. Similarly, let us consider other points B, C, D and T. All these points give out spherical waves. The common tangent of all these spherical waves gives the new wavefront. These spherical waves are called secondary wavelets. If the given wavefront is a plane wavefront, we can draw the spherical waves as shown here. The amplitude is maximum in the forward direction. That is the assumption made by Huygens, and the amplitude is 0 in the backward direction. That is why we are considering the forward envelope. Now let us explain reflection on the basis of wave theory. Let us consider a plane mirror Mn. Consider two rays, one incident at A and the other incident at C. Let us draw the incident wavefront. AB represents incident wavefront. It is a plane wavefront. The part of the wavefront at A gets reflected, while the part at B has to cover a distance BC before gets reflected. So when the secondary waves from B travel through a distance BC, the waves from A travel through a distance AE in the reflected direction. So CE represents the reflected wavefront. The distance BC is equal to distance AE, that is equal to speed of the wave into time. The angle between incident ray and the normal is the angle of incidence I. So the angle between incident wavefront and the surface is I. So let us consider the triangle ABC. It is a right angled triangle. Let us find sin I, which is equal to opposite side BC by hypotenuse AC. The angle between the reflected wavefront CE and the surface is the angle of reflection R. So consider the right angled triangle AEC. Sin R is equal to AE by AC. So sin I by sin R is equal to BC by AE. But BC is equal to AE is equal to C into T, where C is the speed of light wave and T is the time taken. Therefore, sin I by sin r is equal to 1, or sin I is equal to sin r, or I is equal to r. That is, angle of incidence is equal to angle of reflection. Now let us see refraction on the basis of wave theory. Let us see the first case, rarer to denser medium. Light travels from a rarer medium 1 to a denser medium 2. So the refractive index of medium 2 is greater than the refractive index of medium 1. But the speed of light is less in the denser medium. Speed of light in medium 2, that is V2, less than speed of light in medium 1, V1. Consider a plane wave incident on the surface. AB represents the plane wave, incident wavefront. The part of the wavefront at A gets refracted, while the wavefront at B has to cover a distance BC. So when the wavefront covers a distance BC, the secondary waves from A cover a distance AE, which is equal to V2 into T. V2 is the speed of light in medium 2. But BC will be equal to V1 into T. V1 is the speed of light in medium 1. So CE represents refracted wavefront. Angle between incident wavefront AB and the refracting surface AC is I. So consider the right angled triangle ABC. Sin I is equal to BC by AC. BC is V1 into T, that divided by AC. The angle between refracted surface and the refracted wavefront is R. So let us consider the right angled triangle AEC. Sin R is equal to AE by AC. AE is V2 into T. But V2 less than V1 and N1 less than N2. Therefore, sin I by sin R is equal to V1 by V2, which is equal to N2 by N1. A refractive index of second medium with respect to first medium. And this is Snell's law of refraction. Now let us consider the second case, that is refraction from denser to rarer medium. The medium 1 is denser while the medium 2 is rarer. So the distance covered in medium 2 AE will be greater than the distance covered in medium 1 within the same time, that is BC. AE is greater than BC. AE is speed of light in medium 2, that is V2 into T, while BC is V1 into T. V2 greater than V1. So AB represents incident wavefront and CE represents refractant wavefront. So in this case, sin I is equal to BC by AC. BC is V1 into T. And sin R is equal to AE by AC, and AE is V2 into T. Here V1 less than V2 and N2 less than N1. N2 is the refractive index of second medium, less than refractive index of the first medium. Therefore, sin I by sin R is equal to V1 by V2, that is equal to N2 by N1. As the light travels from denser to rarer medium, angle of refraction will be greater than angle of incidence. And when the angle of incidence reaches the critical angle, angle of refraction becomes maximum, that is 90 degree. Therefore, we can write the equation as sin IC by sin 90 is V1 by V2, that is equal to N2 by N1. But sin 90 is 1, therefore we can write sin IC is equal to N2 by N1, or that is equal to 1 by N12. If N2 is equal to 1, the second medium is air, and N1 is N, refractive index of the denser medium is N, then we can write sin IC is equal to 1 by N. IC is the critical angle. If the angle of incidence is greater than the critical angle, total internal reflection takes place. Now let us see the action of a prism, behavior of a prism. A plane wave is incident on the prism. The part of the wavefront passing through the base has to cover more distance through the prism. Here the speed of light is less. So the total distance covered by the wavefront passing through the base of the prism will be less, or the wavefront get delayed while passing through the base of the prism. So the emerging wavefront is tilted towards the base. Let us see the behavior of a convex lens. Here the portion of the wavefront passing through the center of the lens has to cover more distance through glass, where the speed of light is less. So the waves get delayed. So the emerging wavefront is a spherical wavefront or a converging wavefront. Now let us see the behavior of a spherical mirror. First one is a concave mirror. The incident wave is a plane wave. The part of the wavefront moving towards the center pole of the mirror has to cover more distance to get reflected due to the curvature of the mirror. So the wave reflected from the center of the mirror get delayed. So the reflected wavefront is a converging wavefront. But in the case of convex mirror, the part of the wavefront moving towards the center has to cover less distance. So the reflected waves cover more distance. So the reflected wavefront is a diverging wavefront. Thank you.